I'll start off just while I'm talking a little bit. I'll play a demo of a retro game that I've been working on for a couple of years now. This is a demo that I put out in 2022. I'm just going to fast forward a little bit, kind of skip through the text. Don't worry about it. So I've personally been a retro game enthusiast since I was a kid. You know, when I was maybe 13 years old, I literally saved up pocket money to buy an NES off of eBay. And I was getting like cartridges. My local GameStop had like a cartridge bin of NES cartridges, which is kind of crazy to think that, I don't know, GameStop was carrying those. And that was like, you know, when they were on their way out. They were just trying to get rid of their old stock. But I was happy to like peruse that bin and, you know, buy NES games. And, you know, I'm sure if you're here, then you're probably a retro enthusiast as well. It's kind of what this place is all about. And, you know, I'm kind of curious while, you know, I just played through this demo, you know, I just want to talk about retro consoles a little bit, you know? Like, what did you grow up with? Like, any fans of NES? You know, you could just raise your hand or something if you're like a particular fan of this machine, like it's your favorite, you know? Who would say NES is like their favorite retro console? All right. Then how about Super Nintendo? Yeah. All right. Let me see. I want to make sure that this is like kind of against my mouth while I'm looking at the screen here. How about Sega Genesis? Anyone? Awesome. Okay. Now let's start to get a little bit spicy. How about Commodore 64? Is that anyone's favorite retro system? No? All right. How about Amiga? That's my personal favorite. Still getting 0 hands. Oh, someone's scratching their head. Okay. Yeah, you're probably right. Or whether or not you're from England, because that was what it was when I did this talk in PAX. There was one guy who was overseas, and his favorite was the ZX Spectrum. And I don't even know how many of you have heard of the ZX Spectrum. Just raise your hand if you've heard of it. Honestly, okay. Yeah, like. Oh, do you? All right, cool. Then let's move to raising your hand if you haven't heard of some of these. So raise your hand if you have not heard of Amiga, for example. Haven't heard of it, okay. The game that I'm playing right now, the one I'm working on, is for Amiga. And this is a computer that came out in 1985. So that's what you're seeing right now is a game unbelievably running on a machine from 1985, and it's doing this much, all the particle effects and the bullets and everything. And that is a testament to not my skills as a developer, although maybe a little bit of that, but also the fact that you can do these things with these old machines is a result of the advancements that we've made in our programming knowledge, our tools, the availability of knowledge, and of course our skill in game design. That's the reason this sort of stuff is possible nowadays. It turns out that these old systems, we don't have to leave their games library at where they are and, you know, have these nostalgic memories of our favorite games like Super Mario Bros. 3 and, I don't know, Chrono Trigger. You know, these games are masterpieces. They never stopped being fun, but the fact is that we can continue building upon these libraries and making new experiences for our favorite old systems. And that's what this talk today is going to be about. I'm going to show you that it's easier than ever to develop these games. The tools are readily available and very well supported. There's fantastic communities of people who are doing this sort of thing and who are happy to help out whoever's interested in developing for these systems. And there's benefits beyond just as a hobby, you know? Like if you're an aspiring game developer, which, you know, raise your hand if like you're interested in maybe making your own game one day. Literally everyone. There are reasons to consider making a game for a retro system, even aside from just being a retro game enthusiast. So, you know, it can possibly, depending on who you are, what your background is, it could literally make business sense to make a retro game, as opposed to like a modern game and just throw it on Steam where the market is completely saturated and it's not going to get any attention at all. You know, sometimes the more narrow you get with your target market and the system you're targeting, the more attention it's going to get because the group you're targeting is that much more enthusiastic about their favorite stuff, you know? And the Made as a whole, I think, is a testament to that. You know, everyone here is so enthusiastic about retro games and machines. So let me see. And, you know, I find it interesting that so many games nowadays, especially in the indie space, they're like these pixel art games, and some of them kind of push it to new limits. You know, you look at, I don't know, random example like Octopath Traveler. That's like pixel art, but they're doing crazy awesome stuff with the lighting and the pseudo 3D. But other games like, I don't know, Shovel Knight, for instance, Bloodstained Curse of the Moon, they're actually trying to adhere to the limitations of the systems that they're mimicking, like NES, for example, you know? It's in style to do this, and there's really there's no reason we can't make similar experiences on the real hardware that we're mimicking, you know? It's like there's proof that people like this stuff. These are popular games, and so it only makes sense to consider the real hardware as a target for that. So before we get started, I am not literally the most qualified person to be giving this talk because there's people who have like done a lot more developing for these platforms than I have, you know. And I've primarily been working on Amiga as my own platform, but I know enough to demonstrate stuff for other systems, for simpler systems, and that's what we're going to be doing today. So, you know, there could be people watching this talk afterwards or maybe online who are mad that I'm not doing as good a job as they would be, but you know, I want to do what I can because I just want to share this joy and this knowledge and path to entry with people. So that's kind of where we are. But there's so many resources out there that I simply cannot cover them all. I can just show you some of the ones that I'm familiar with. So I talked a little bit about why you might want to consider making a game for a retro system. The fact is that you know, you get to be a part of a community of enthusiasts, you know, and you get to not only share that enthusiasm, but they're so delighted for anything that's put out for their systems that you're kind of guaranteed to get some attention and people there supporting you, as opposed to just throwing your project into the void. There's another interesting reason, which is that limitations can breed creativity. This is something that we hear a lot. And it is extremely true, I think. I was talking to my friend Arda, who's in the front here, on the way here, about how as game developers, sometimes the fundamentals of what we're making can kind of escape us. It can be hard to really ask yourself what makes a game fun, you know? There could be two very similar games, you know? Like, they're both an adventure game. They both have a combat system with combos. They both have crafting. I don't know. And you put them side by side, and one of them is extremely fun, and one of them is not so fun. And it's really hard to ask yourself, like, why is this game not as fun? You can sort of speculate, but it's almost like the ingredients are there, but something is separating these two games from being fun and not fun. And it gets sort of muddled just because there's so many advanced and complex systems piled on top of each other nowadays. But when you sit down and you make a game for an 8-bit system that only has a few kilobytes of memory and you can't do all that much with it, you really have to sit down and ask yourself, like, what is a really simple way that I can make this game fun? And that is just the laser focus of the project. And so I think it's a great learning experience as an aspiring game designer as well, because that's the only focus of this project, aside from learning how to program and all that. But there's just so much focus on the little bits of gameplay that you do have in there. You really have to ask yourself if it's fun and what makes it fun. And you really just have to capitalize on those. And that's something I really believe in myself as a game designer, is figuring out what the most appealing aspect of your game is, the actual fun part, and everything about the game being for the purpose of supporting that component that's fun. So I think developing for retro systems is a really great way to make that happen. There are also reasons that you wouldn't want to develop for a retro system, and that is, in general, it's a greater barrier to entry, right? It's a little more difficult. It's a little bit of a slower process. Oftentimes, if you do have an idea for a game, you can boot up Godot or Unity or something, and in like a few lines of code, you can get like a basic prototype going, kind of. But with a retro system, there's a lot more stuff that you have to worry about because none of that work is done for you behind the scenes. So there's a little bit more of an obstacle if your goal is to just make a game. Just take your ideas and put them onto the screen. There's a little more of an obstacle there. There's more problems you have to solve. However, if you are a problem solver and you like solving problems, it is fun and addictive to make games for these platforms, I can say that. But yeah, that's the general reason why you wouldn't want to pick a modern platform as opposed to a retro platform is they allow us to put more of our effort into the design of the game and focus on building things as opposed to solving programming problems and all of that. But I do think that building games for retro systems has more merit than people think. It's like this. People treat it as this obsolete, thrown out, nostalgic thing that you would only develop for it just as a hobby, like as a hobby project, and then it's just a curiosity that people forget about. But then you're also seeing some companies who are literally selling their new retro games, and they're successful. And we can definitely do more of that. There's clearly a market for it. Okay. Let's write some code, I think. Let me double check my notes. Okay. I'll get to this in a second. First, let's jump over to here into our Commodore 64 emulator. Welcome to Commodore 64. The maid has these downstairs as well if you want to check them out. You boot up the system. This is the screen that you're greeted with right when you boot it up. It takes 1 second to boot, brings you straight to this screen. This is all it is. If you want to make this computer do stuff, you gotta program it. That's just the way it is. But there's kind of a joy in that. The computer it's completely unprotected. The whole system is just wide open. I mean, I can use the poke command. This is a classic Commodore 64. I can talk to memory address 53280. The whole memory space is wide open. You could do literally whatever you want this computer. I can say put 4 in that memory address and hit enter. There it is. I made the background pink. You could do just literally whatever you want. And then here's the classic 20 go to 10 program. Not echo, print. 10 print hello, 20 go to 10. So very simple program. We're line number 10, I'm printing hello. Line number 20, I'm going back to line 10. So as soon as I run this program, it's going to print hello over and over and over again. And that is our very first Commodore 64 program. It's that easy. But if you want to take true control of the machine, you can't use this sort of built-in friendly interface to mess with the machine. You have to get down and dirty, and that's what we're going to be doing today. We're going to be writing in assembly language. Raise your hand if you have at least heard of assembly language. Okay, so we all know what's up. Assembly language is, you can't really describe it as a programming language. What we're going to be doing is we are literally sending instructions directly to the CPU on this computer. So there is nothing between us and the processor. We're telling it exactly what to do, and when we run this program, the only thing the computer is doing is running our code. It's a very intimate relationship, I guess you could say. So let me explain what we have going on here on the screen. So at the top, I'm bringing a couple of other files that I wrote that I'm not going to go over. They're sort of just like startup files, that are routines for like starting the program, nothing too special. So, and here's what we have. I have a routine called setup, and I have a routine called main loop. So what the computer is going to do is when my program starts up, it's going to run the setup routine. So if we need to if we need to do any housekeeping at the start, let's say I have a character and I want to set his position to position 100 or whatever when the program starts up, we're going to put that in the setup routine. And then the main loop routine is going to run every frame. So that's going to be where our logic goes, and if we want to do jumping or moving objects or whatever, then the main loop is going to run every single frame, which is about 16 milliseconds, I would say, is one frame. And we have one instruction here, RTS, that basically just means I'm done with the routine, send me back to where I came from. So, as you can see, there's nothing happening right now. It runs setup and it says, okay, we're done. And then every frame it runs main loop and it says, okay, we're done. So if we run this program, it does nothing. The program is running, and every frame it's running that main loop, and then it's just doing nothing. It says I'm done right away. So this is what we get. We just get nothing. And by the way, my development environment is nothing special. I'm running Visual Studio Code, which is free and ubiquitous. It's kind of what everyone uses for programming nowadays. And I got an extension for Commodore 64 development. People are making VS Code extensions for developing for these retro platforms, and it does a lot of the formatting for you, syntax highlighting. It gives you, all the little nice tools that you would want in your little programming environment. So let's start filling this out. Let's make some stuff happen. How about we put a sprite on the screen, right? We want a character. So yeah, let's go ahead and do that. But as part of that, I need to kind of explain how a computer works. So I hope you brought a snack and you went to the bathroom, because we're talking about how a computer works. Computers are very simple. They have a bunch of memory. The CPU, it takes numbers from the memory, does arithmetic on them, and it puts them back into the memory. And that's pretty much all it does. That's the way a computer works. And then there's a special video chip, and if you have to draw something on the screen, you talk to the video chip. But that's pretty much all we're doing. We're just manipulating numbers, and then by magic, stuff happens on the screen. But these old systems, they're so simple that we can actually understand those steps, we can understand everything that the computer is doing, which is part of the joy of this. So here is what we're going to do. I demonstrated before setting the border color. So let's just set the background color for our game. So I'm going to, let's see, we want to make the background white, and we're going to make the border light blue. So here's what I'm going to do. I'm going to load white, and I'm going to store it in special memory address. This is going to be D021, and I'll explain this in a second. Okay, so here's what we're doing. I'm loading, that's the LD for load. I'm loading the number for white, which is number 1. And then I'm storing it in this address. I like to think of memory in a computer as like a mailroom. Every mailbox has a number associated with it, kind of like a house number, right? And inside every mailbox, there's a number. Every mailbox just holds a sheet of paper with a number written on it. And we can take the number out of that mailbox. We can change it. We can put it back in. We can put a new number in the mailbox. It's literally all memory is. It's a mailroom with a bunch of mailboxes. So this is a special mailbox. It's owned by our friend Vic. And Vic runs the video on the Commodore 64. And his street is street D0. So he has a special mailbox for the background color and a special mailbox for the border color. So when I take the number 1 and I put it in this mailbox, then Vic sees that and says, oh, let me change the background color for you. Likewise, for number 20, he says, oh, let me change the border color for you. So that's pretty much all we're doing. We're loading these numbers, loading number 1, putting in that mailbox, and then light blue is number 14, and we're putting in the next mailbox. So let me go ahead and save and run this, and if all goes well, we will see the colors change. There we go. So our border is light blue and our background is white, and this is going to be our play field for the game that we're making. Is anyone confused yet? No. What's that? Oh, I'm sorry, I couldn't hear you. Yeah. VIC is a video chip that lives on the Commodore 64. So when I choose an address, on the circuit board of the Commodore 64, when I send out this, when I send out this number to go into a mailbox, somewhere on the circuit board, there's a special piece of logic that looks at this D0, and says, okay, this needs to go to VIC. And then VIC is another special chip on the Commodore 64. So the number goes to VIC, and VIC is hooked directly up to the wiring that goes out to the TV. And so VIC's job is to control the screen. So when VIC receives this signal at number 21, that sets a special, it gives him a special signal to change the background color in the border. So that's pretty much what's going on there. It's the name of the video chip on the Commodore 64. And it is, in fact, called the VIC. I think it probably stands for Video Interface Chip or something like that. Yeah, okay. Awesome. So yeah, we're going to be talking to VIC a lot because that's how you get graphics on the screen. And next up, we're going to be drawing a sprite. Sprite is a very ubiquitous term that we still use nowadays. Typically, if you have a game, a 2D game that has any graphic, like the character, whatever, we call that a sprite, But sprites were a little bit more special back in the day because computers have gotten so fast that every single frame, we can redraw the entire screen, You know that a screen is a grid of pixels, right? So every single frame, we are just completely redrawing every single pixel on that screen. And there's like millions of them, and we're just, pumping them out because computers have gotten so fast. But back then, you couldn't do that, That's a lot of pixels, and the CPU is really slow. It can't update every single pixel every frame. So to get around this, our friend Vic has sprites. And that means what you can do is you can give Vic a graphic of a character, just a little pixel art character, and say, hey, here's my sprite. And the Vic is like, okay, I'll remember this. And then you tell it where you want it to draw on the screen, I want to draw it at X 100, Y 100. And then you just tell that to Vic, and Vic is like, okay. And so now every frame, Vic is special purpose designed to take this graphic that you gave it and wait until, it gets to the screen region you want to put it in and draw it in that spot. So sprites and, tiles, which, retro games are also associated with tiles. These are all for the purpose of not being able to draw the whole screen pixel by pixel every single frame. It's like a clever way of getting around that when computers were not yet powerful enough to do that. Okay, so I'm just going to make a little note here. Set background colors. These are convenient little ways of annotating what your code is doing because it is not necessarily easy to read at a glance. So let's set up a sprite. First thing what we're going to do is we are going to load a number. Number 1, effectively. And we're going to store it. We're going to talk to Vic again. It's Vic because it starts with D, right? And we're going to write into, where is it? 15. 15 is Vic's special mailbox that tells you what sprites you want to use. And as you might be able to infer, this just says, I only want to use sprite number 1. If I wanted to use 2 sprites, I could enable sprite number 2 like that. If I wanted to use 3 sprites, I could enable sprite number 3. Right now, we only want 1 sprite. We just care about the character, our player character that we're drawing. So let's see. So we are enabling sprite number 1. We don't have any graphics yet. We're just telling Vic, hey, we want to use this sprite. But we're going to give it a graphic. So we're going to load a special section called player sprite. I made this in my graphics file. You see at the top I'm importing. Oh, how do I make that go away? Oh, man. Hold on. It's probably this. Okay. I don't know how that popped up. But anyway, so yeah, I set up some graphics ahead of time before this presentation. And I have a graphic called player sprite. So I'm just going to take that. I have to divide it by 64. It's just a quirk of the Commodore 64. And we're going to store it into this special memory address, which is a space where Vic looks for sprite graphics. This is stuff that, you know, when I'm talking to Vic and I'm like loading these special addresses that look like just random numbers to all of you, these are specific to the Commodore 64, and you can find like, you know, a wiki and a manual that just explains all of these addresses and what they do. It's every single Vic address for all the colors and all the sprites and, you know, the video formats and the tiles and everything that you want to do with Vic is just laid out. It tells you what these addresses do. I just have them in my notes, and you're not expected to memorize these. You're going to have a page of notes as well that tells you what all these addresses do. And so this address right here is specific to telling Vic where to find your player graphics. And this will become a little bit more clear in a second, you know. These are going to turn into actually nice-looking names instead of just random numbers. But for the time being, we're dealing with the random numbers. And let's set the player to dark gray as well. I'm sorry. And that is going to this position. 27 is the address that Vic uses to control the sprite color for this sprite. Okay, so we set the sprite graphic. We enable the sprite up here. And let's add better comments here. So we're going to do enable sprite, set sprite graphic, set sprite color, set sprite position. That's what we're doing next. So let's just say position 100. The screen is about, what is it? It is about 320 pixels across and 200 pixels down. So position 100 should be like maybe a third way from the left of the screen and maybe halfway down the screen. That's what we're looking at. So we're going to store that in these two addresses. Which, again, we're talking to Vic. This tells him the X and Y position for our sprite. So, quick recap. I think it's still pretty straightforward. Most of this is just talking to Vic and his special addresses, but we have the background colors that we're setting. We're telling him to enable sprite number 1. We are telling him where to find our sprite graphic, which is in this data that I set up ahead of time. Then we're telling him to set the sprite color for our sprite, and then finally setting the sprite position. So if nothing went horribly wrong, we should be able to run this. And there he is. Oh, thank you. So yeah, we're going to be making the Google Chrome dinosaur game on the Commodore 64. Or I should say a cheap imitation of the game. We would be here all night if we were going to make the entire game, you know? But we're going to get far enough to make something playable. And my goal is for you to be able to understand all of the logic that's going on as that's happening. Yeah. I want to ask if there's questions, but, you know, there's probably going to be a lot of questions at this point, but go ahead. The source file for the player sprite is this file. Yeah. See, here's my label player sprite, and I'm just giving it a bunch of bytes. In fact, you can sort of see the dinosaur in there, right? Just drawn with the ones. Yeah. So it's just zeros and ones, right? 0 says there's no dot. 1 says there's a dot. So I literally just drew the dinosaur out of bits. And that's that. And the computer's looking at those bits, and it's just drawing into the screen. It's kind of funny how simple it is, you know. So yeah, that's the graphics file. I just prepared that ahead of time. Those are built into the Commodore 64. Vic has 16 colors. Each number from 0 to 15 is assigned to a color. Yep. The comma is just formatting where, yeah, let me bring that up again. So In this assembly language, I'm giving it bytes, and a byte is 8 bits, right? And so the commas are separating these into bytes, basically. So there's going to be 8 bits, 8 bits, 8 bits, and that's why the comma is there. It's just the assembly language doesn't understand like a big string of bits, to my knowledge. Maybe some assembly languages do, but this one in particular likes to work with bytes. There's another graphic, but we'll get to that later. It's a secret. Okay, let's. How about we make our dinosaur move? That's kind of important. You need moving stuff in a game. But I think before that, I was talking about just all these magical random numbers. It is, I mean, I have these nice commented annotations, right? But that doesn't necessarily make this easy to read, you know? I'm like loading 100, and then I'm storing it into D0, 0, zeros, and D001. It's like, you know, if you've been programming for this machine for 10 years, like you might just have those memorized and intuitively know what it's doing. But you know, we don't have that luxury. So how about we give some of these numbers names? That would be nice, right? And that's what we're going to do next. So all the way up here, I'm going to come up with a name. Let's just say Sprite Player X is what we're going to call it. And that's this number. Let's make another one. And that's this number. So now these numbers have names, and what we can do is down here, instead of this random number, we can put Sprite Player X, Sprite Player Y. And again, unless something goes horribly wrong, this should just like build, and it should look the exact same as it was before, because it's doing the same thing. We just gave this number a name, except now we can actually read what's going on. You know, it's almost resembling a real programming language. What do you know? So now we have names for this, and we're gonna add more names as we go. You know, for the sake of time, I'm not going to name literally every single thing here, especially the things that, you know, like the background. We're only setting this once, and then we're done. So I think it's like, you know, kind of clear enough what's going on there. We don't have to name literally everything if we don't want to. But let's see. We need a place to store our character's position. You know, we have the sprite X and Y, but that's just telling Vic where to draw it on the screen. We need a mailbox, to use my other analogy, to store the position. And so as we're playing the game, we can take that number, we can add to it and move it around and then put it back in that mailbox. We need a storage spot for our position. So I'm just going to make a number called position, and let's put it at, we can put it wherever we want. I'm going to put it at address 2. That's what's going to hold our position. So now we have a spot for the position, and we want to take our 100 and we want to store it in that spot as well in the setup. Okay. So now we finally get to, you know, do actual game logic, make stuff move on the screen. So now we're in the main loop. Again, this is the routine that runs every single frame, you know? So if we want to make something move, we need to do something every single frame to move its position across the screen. So let's, you know, just as a little test, every frame, let's increment position. That's what INC means. It means increment. We're just adding 1 to it, you know? So it's going to start at position 100. Then next frame, it's going to be incremented to 101. Next frame, incremented to 102. And now we need to take that value. We're loading it. You know, we're taking it from the mailbox, and we're putting it into the Y position. Our dinosaur, he doesn't move left and right? He only jumps up and down. So we're only concerned with the Y position. The X position is not going to change. So here's our little test. So if everything works here, every frame, we're going to increment the position by 1 at a time every frame. Let's see if we accomplish that. There he goes. Bye. Oh, he's back. So, okay, a couple things that you might notice here. One is that we're incrementing the Y position, but he's actually going down, right? We're used to thinking about graphs where the Y-axis is upwards, but these old systems, when they draw the screen, it draws from top to bottom. So the top of the screen is line 1. The bottom of the screen is line, let's say 200 or whatever. And so that's why incrementing the position sends it downwards. You know, position 0 would be at the top of the screen. Position 200 is at the bottom of the screen. The second thing is you see him wrapping around the screen. And this is actually, you know, old games are kind of famous for this, right? The screen wrapping. Oftentimes it happens as a glitch or something like that. And it's because this value, it's an 8-bit value. That means it can only store a number from 0 to 255. If you try to go higher than that, you know, up to 256, it just wraps back around to 0, you know? If we want to think about it in base 10, you know, let's talk about like 99 and 100. Let's say you can only store 2 digits, right? Well, you get to 99, you add 1 and get to 100. Where does that third digit go? You can't fit it anywhere, and so you just have the 2 zeros and you're back to 0. So that's quite literally what's happening here. It's trying to, you know, we're incrementing it to 256. It can't store that extra digit, and so it just wraps around to 0. And there is a good explanation for that. And there are ways of getting bigger numbers, and we're going to have to do that a little bit later on. But for the time being, we're working with these 8-bit values that have this, this cutoff point. But in general, we only have, I don't know, like a few lines of code here. I mean, this is all set up, and then we have 3 lines of code, 3 instructions that we're sending to the processor to just say, like, to do some arithmetic on these values. And we have a character moving on the screen, you know? It's pretty amazing if you think about it, how simple it is. Especially for assembly language. Like, assembly language has this reputation of being some kind of black magic or sorcery that's impossible to understand. But if you just break it down like this and you work with a nice and simple 8-bit system where you can kind of understand what's going on, it suddenly makes sense, and hopefully it looks a little bit less scary than what you imagine it might be. So we want to set up subpixels. And I'll explain that in a second, but the problem is what we have set up right now is, you know, he's moving 1 pixel per frame, and I mean, he's not going fast, right? But you can't imagine this is the absolute slowest that we can make our character move, you know? Like, that's 1 pixel per frame, and then, you know, if I increment the position twice per frame, then now he's going to move 2 pixels per frame, right? So now he's moving twice as fast. But there's no in-between. We want a nice smooth jumping motion when he moves, right? So if you can only move this fast or half as speed or 3 times as fast, those are, the speed gaps are too large in order to give us a smooth movement. So we need fractions. We need fractional pixels. Like, how do you move him half a pixel per frame, right? That's kind of what we want for something like a smooth jumping motion, because he has to be moving up, slow down smoothly to 0, and then start coming down and speed up smoothly in the downward motion. So we are going to set up a fraction. Let's take our position, and this is now position low, so that's like the fraction. And we're going to set up position high. Let's just put that in address 3. And that's going to be our pixel position value. And we need to make sure we change this here. And look at that. Thanks to VS Code, I renamed positions, so now it gives me the little red squiggly warning me that name doesn't exist anymore. So we're going to do that. And oh no, this is now position high. And then we're going to load 0 and store that in position low. OK. And let's just delete the increment for now. And then, so before we were taking the position and loading it into the sprites Y, we just renamed it to position high. Again, that's our name for like the pixel position. And then position low is going to be the fraction. And we probably also want a gravity value, right? So we're just going to name that like grav, and we'll just make it the number 10. I don't know like how the physics are going to work, but the nice thing about naming these numbers is in my code I could say add the gravity, and then if it's too floaty or not floaty enough, then I can come back up here and I can just change this number later to whatever I want. And that's probably what we're going to end up doing. We're not going to get the physics right on the first try. So let's set up a physics routine. Now, with physics, you have your character's position, you have their velocity, how fast they're going, and then you have their acceleration, which is like gravity, basically. And the way physics works is you add the acceleration to the velocity, and you add the velocity to the position in order to get the character to move. And the same law applies in games, and so that's what we're going to be doing. Which means we also need to remember the velocity values. So, pretty similar. Velocity low, we're going to have a fraction. Just put it there. And then velocity high, put it there. And again, these addresses, like 2, 3, 4, 5, I can store these wherever I want, as long as it's within like the bounds of the Commodore 64's memory. I'm just picking these addresses because they're very simple, and that those spots are available to me. Okay, so we have addresses for our position and velocity, and we have some value for gravity, which is just 10. So let's go back down here. And we want to keep this here. This is like, that's how we take our position and write it to the sprite. So that's always going to happen in our loop. We always need to update the sprite with our latest position. Let's make a new routine. Let's call it physics. And the routine always ends with RTS. Again, that's what says it's the end of the routine. And I'll show you how to use this routine later on. Because again, right now the program, it only knows how to run main loop every frame. So how do we get it to run physics? We'll do that in a second. But for now, let's write the physics. So we're going to start by adding the gravity to the velocity. And then later on, we need to add velocity to position, right? And that's pretty much it. After that, we have ran our physics. All right. This is the part that's a little bit hard to explain. I'm going to kind of write it out first and do my best to explain it. So we're taking the velocity, the velocity fraction, and we're adding our gravity to it. Straightforward so far. Grabbing the value, ADC means add, right? So we're taking our velocity, adding the gravity to it, and then we just need to put it back. Here's the part that might throw you for a loop. So this is the fraction, right? So let's take the whole number, velocity high, and this needs to sometimes have something added to it, right? Like if the fraction overflows to, if we get from 7/8 to 8/8, then we need to take the whole number and add 1 to it, right? So what is the logic for that? It sounds pretty complicated. This is what we do. We're adding 0 to the velocity. And this is where we introduce our new friend. Her name is Carrie. And Carrie has a special job. When there's an overflow in the numbers, again, I was talking about it before, it's like you get to 255, 256, you have nowhere to store that extra 1 and it just goes back around to 0. I was kind of lying because that extra 1 actually goes off to our friend Carrie, and Carrie holds on to it for us. And that's the secret of this add instruction. It's not just add, it's add with carry. So what that means is we're adding 0 here, but if carry happens to be holding a number, a 1, then carry is going to add that in as well. So that means, again, we're adding the gravity to our fraction, and in this case, the gravity is 10, right? And we're storing it back. But let's say our fraction was at, I don't know, 250, right? We add 10 to it, and it rolls over past 256 over to 0. So that extra 1 goes over to carry, and then we're storing the fraction, which again it's like rolled over back to 0. But carry's still holding on to that extra 1, right? So now we're taking the whole number, velocity high, and when we add 0 to it, well, carry has that 1, and it's being brought over into the whole number, and then we're storing the whole number. So this is how you do math on numbers, bigger than 256 on these old systems. They have a mechanism to remember that extra 1, the carry, and hold on to it, and then you take the bigger portion of the number and you bring in the carry, Pretty similarly to how we, do math by hand that we learn in elementary school is, if there's an overflow in one column, then we write the little carry number over to the next digit and we add those in. That's pretty much what the computer is doing here, the exact same thing. Is this clear enough to everybody so far? Is anyone scratching their head? We generally understand what's happening. If you don't have a full understanding of this, then that's completely fine. But that is generally, that's probably the most complicated thing we're going to be doing in this program. So, don't worry so much about it. So we added the gravity to the velocity. Now we need to add the velocity to the position. So we're going to take the velocity low, the fraction. Sorry. We're taking, actually, I guess it technically doesn't matter. No, we're going to take the position fraction. And we're going to add the velocity to it. And then we're storing it back. And now it's the same thing with the whole number. We're adding the whole number velocity. Sorry, my glasses keep on rubbing against this microphone every time I move my head. I hope it's not that annoying. Okay. So that's pretty much it. Again, we're just grabbing the position, adding the velocity to it, and then putting the position back. And I said before, that's all these computers are doing. You're taking numbers out of the mailbox, you're doing arithmetic on them, and you're putting them back in the mailbox. And that's all computers do. So if everything is correct, we have our physics routine. There's just one tiny little extra detail I have to add, CLC, which clears the carry. It tells carry to drop whatever she's holding from before, because she'll always remember that number. If I'm off in some other physics routine or I'm adding numbers somewhere else, like carry diligently holds on to that 1. So when it comes time to run the physics, we want to make sure that her hands are free. We're kind of like resetting her, and so that's what that's doing. And if people have programmed for this system before, they might get pedantic, like, oh, you can save a few CPU cycles by not clearing the carry here. But just we want to be diligent. We want to make sure we don't have bugs. And so we are, whenever we're ready, whenever we're making use of the carry bit in this way, or even just doing this add operation, we want to make sure that the carry is clear. Okay. So the very last thing we need to do here is we need to run this physics routine, right? It's just sitting there. Like I said earlier, it's only the main loop that's running. So we need to run this physics routine. And that is very easy to do. Run physics. It takes one instruction. And it's JSR. It stands for jump to subroutine. And that's it. You do JSR physics, and the computer behind the scenes, it remembers where we are. It remembers, just let's say line 38, and it's going to jump down to physics, run this routine, and then we hit the bottom, return to sender, as it's called. It actually remembers, hey, I came from main loop line 38. So it jumps right back to where it came, and then it continues on. And it's that easy to organize your code into these nice little routines. So finally, I've done enough talking and coding. Let's see this in action if our physics routine actually works. Oh my God, he's going crazy. All right. So we clearly need to adjust some parameters here. And let me make sure I don't have any bugs, because I don't think he's supposed to be moving this fast. I'm working with fractions, right? I know what I did wrong. I forgot to set those values to 0. I'm pretty sure that's what's going on here. I think. So that's another interesting thing about this old software. Like, back up here, these velocity values, I'm saying, hey, address number 4 and address number 5 are our velocities. Well, when our program starts, those addresses could be holding anything. The computer's not guaranteeing that they're all empty for us, Whatever the computer was doing before, it was probably using those addresses for its own housekeeping stuff, whatever. And I think this was my mistake here. We need to make sure they're empty. We're starting with a clean slate. Let's see what happens. There we go. Okay, now it's working properly. And we get to see him slowly speed up and speed up and speed up. Anyone play Portal before? Yeah, that's what this reminds me of. Okay, but we don't want this to wrap around forever, right? We want it to stop when he hits the ground. That's what floors are supposed to do. So I think that's what we're going to do next. We're going to call this the clamp routine, because clamping in computer science land typically means, you want to make sure that a number doesn't go past a certain point. If it starts going past it, you clamp it back to that value. So that's what we're going to do next. And we need a new number for that. Where's the floor position, right? Or in this case, let's call it position max. It's the maximum position that our dinosaur can go. It can't go any lower. And we're going to make that 228. I know this number because I tested this ahead of time, and that's where we want the floor to be. It's like somewhere close to the bottom of the screen. But now we need to write some logic for the clamp. It's not trivial, because if you think about it, there is logic there, right? It's like, if he's above the floor, then you just want to run the physics as normal, But if something sends him below the floor, we have to catch that, and we need to put him back where the floor is. So that's what we're going to do next. We're going to write a routine called clamp. And let's get started with this. We are going to make a comparison for the first time. So we're going to take the position, the whole number position, the pixel position. We're going to compare it to the maximum position. And if our dinosaur's position is lower than the maximum position, and again, lower means upwards, lower means higher, then we don't want to do anything, If he's higher than the floor, then we just run the physics as normal. And that's going to be BCC. And I'm going to write, a little label called end here. And let's just make that now. I'll explain this in a second. And again, our RTS goes at the bottom of every routine here. It says we're done. So I'm just adding this here. And so what this is going to do is, again, we take the position, we compare it to our maximum position where we want the floor to be, and if it's less than the maximum, then just go back to what you were doing. We don't want to perform any special logic or anything. So BCC effectively means if it's less than. It's slightly more complicated. Not going to get into it, but the B stands for branch. So we're if it's less than, we're branching to end. So we're going to be skipping all the stuff that we're writing here. So past this is assuming that we're past the floor, let's say. Okay. So if we're past the floor, we want to take the dinosaur's position and just put him back on the floor, right? We don't want him under the floor. So that's pretty easy too. We're just taking our maximum position, which is, the floor position, and we're storing it there on the dinosaur's position. There's a little bit more we have to do. We want to clear out the fractions, and we want to turn off the dinosaur's velocity too. When he hits the floor, his velocity hits 0. So we want to take 0, store it in the fraction position, store it in the velocity, store it in the velocity fraction, and that should be it. And we have this new routine called clamp that we need to run here. We're just going to do it after the physics, like that. So again, to recap, we're running the physics as usual, we're adding the gravity, and then after the physics, we're running the clamp. So it's checking to see if the dinosaur's past the floor. If he's not past the floor, then we exit. We skip all of this stuff and we just go right to the end. But if he is past the floor, then we make sure we set that dinosaur's position to where the floor is. We kill off all the velocity and all of that, so he should just stay on the floor. Let's check if this works. Boink, there he is. He's standing on the floor now. Excellent. Okay. So we're getting there. This is almost starting to look like a game, isn't it? All right. Yeah, so who here has programming experience? Even if you just did some tutorials or whatever. So almost everybody, okay. So, yeah. If this is too slow-paced to you, I apologize for making this as accessible as possible. But, yeah, you might, if you're a programmer, you'll notice we're not working with if statements, right? In a normal programming language, you would wrap this in an if statement, say, if the dinosaurs pass the floor, run this code. It's almost like the opposite here. We're running a comparison, and if he's not past the floor, then we're just like exiting, But that's the way it works in assembly language. There's no if statements. You're using these comparisons, and then you're branching depending on what condition you want to check for. Like in this case, I'm branching if it's less than. You can branch if it's 0. You can branch if it's not 0. There's other complicated conditions you can branch for. That's how it works in assembly language. It's all comparisons and branching. And a comparison, by the way, behind the scenes is just a subtraction. It's like subtracting these two numbers and seeing where is it in relation to 0. Is it less than 0, greater than 0, etc. So, if it interests you as a programmer, that's kind of what's happening behind the scenes here, how these comparisons work. Okay. So I guess the last thing that we haven't done yet is he's still kind of starting in midair, right? We want him to start on the floor. So we're just going to do that real quick. It should be pretty straightforward. We'll go back up to our setup routine, and we are going to grab our max position, and we're going to store it in this spot. Before we were storing 100 here, let's just get rid of that. And the player Y position, let's, how do we want to do this? Okay. Because wherever our position starts, we want to make sure the sprite starts there as well. Okay. So let me just double check that. Just want to make sure he correctly starts on the floor here. Okay. Excellent. So what's the next natural thing to do here? We want to make him jump. You can't really have a game without allowing the player to control the character in some way. So we're going to make him jump. And to do that, we need to talk to the joystick. Thankfully, Commodore 64 makes that just about as easy as everything else. And we can talk to the joystick through another special address. We're talking to joystick number 2. That's just convention for Commodore 64. Games are controlled with joystick port number 2. And that is going to be address DC00D. So we're talking to Vic again? No, actually. Vic only does the video stuff. This time we're talking to the CIA. But, yeah, it's kind of toward the end of the D address space, it switches from VIC to the CIA. Again, there's a special thing on the Commodore 64 circuit board that like looks at the address you're giving it and routes it to the correct chip in order to deliver it to whatever part of the system you're trying to talk to. So that's our joystick 2. And we also need, we're going to call it jump force. And let's just start with like 4. This is, when you jump, how much force is the dinosaur going to be sent up? How much velocity are we giving it on the way up? Because that's really what it is when you jump. You're just sending a velocity upwards. So let's just start with 4 and see how that goes. All right. So now we need a routine to, all we want to do, we got to look at the joystick now, right? So if they hit, let's make it the fire button on the joystick. If they hit the fire button, then we send a jump. So we're going to have a routine check jump. And we're loading joystick 2. And here's the interesting thing. Just every direction and button on a joystick, it's just a 1 or a 0. And if we want to see what the joystick is doing, that's all we have to do. We just, same as grabbing a value from a mailbox, except now it's not a mailbox. It's like the CIA has some special wires hooked up to your joystick. And, when you reach into that mailbox, you're kind of reaching through those wires into the CIA special interface, and whatever the joystick is doing at the time, that's what you're getting back. So we want to check if the fire button is being pressed. And this is how we're going to do it. Okay. And I'm not going to over-explain this, but if you're a programmer, you might know what's going on. The joystick has 5 bits, 5 ones and zeros, for up, down, left, right, and fire. The one that I have as a 1 right now, that's the fire button. These 4 zeros are up, down, left, and right. So I'm performing an AND routine, which basically says whatever is a 1 in this number, that's the only value that I care about here. The rest of them are not important. They're being zeroed out. So what this does is it's taking the joystick directions and the fire button, like whatever buttons are being pressed, and it's discarding the directions and only the fire. So everything else is always going to be 0. The fire button is going to be either 0 or 1, depending on whether or not we're pressing it. So let's do another end routine here. We need an exit. So we're taking the joystick and we're putting it through this special filter that says we only care about the fire button. And if the fire button's not being pressed, then let's get out of here. We don't care about this routine. We're not jumping. And again, something pedantic is if the fire button's being pressed, this is actually a 0. If it's not being pressed, this is a 1. That's just how the Commodore 64 works. Things turn to 0 when you press them on the joystick. So B&E stands for branch if not equal. In this case, it means not equal to 0. So that's the full picture here. It's like if the fire button is a 1, it's not equal to 0, so we just get out of here. We move to end. But if it's 0, that means the fire button was pressed, and we're going to continue on. So this is where we make the dinosaur jump. So we're going to take our jump force, and we're going to put it in the velocity. And let's just, for the sake of preventing bugs, let's take that fractional velocity and zeroing it out. Because otherwise, the game might remember that fractional velocity from something we were doing before, and it's not relevant anymore. That happens a lot in old games like NES games. They have this fraction that is not properly cleared when you do a new action. And so it usually doesn't have any noticeable bugs, which is why they didn't fix it. But in Super Mario Brothers, for example, there might be I don't know, sometimes your jump might send you just a tiny bit higher than the last time you jumped. It's because that fraction can stick around, basically. So it's good practice to make sure it's cleared and you get the same result every time. Yeah, but this should be it. It's that simple. When we press the fire button, we add a force to the jump. There's going to be a couple problems with this code, but we'll get to them. And the first one right away is, remember how I talked about how positive numbers are down? So we actually want to add negative jump force to send them upwards. If I really wanted, I could do this, and then up here I can go to the jump force, and I can make this like -4, and that would accomplish the same thing. But I think it's a little bit more clear if we say up here the jump force is 4, and then when we are adding the jump force, we add negative. Either way is fine. This is just the way I like doing it. So if all goes well, oh, I forgot to add check jump up here into the main loop. Let's put it at the top before the physics. Because, if we're jumping, if we're starting to jump, then we want the physics for that jump to happen right away. So this is just kind of like an interesting technicality. If we took check jump and we put it down here after the physics have already run and we're hitting the jump button, but now it has to wait all the way until next frame before it calculates our jump and starts adding that to the physics. So, if we want to make it as responsive as possible to the user, then we'll probably want to check the jump first. It makes 1 frame of a difference, but that still can be the difference between life and death. So let's see if this works. So I don't have a physical joystick, but I've set up the simulator to map the shift key to the fire button on the joystick. Whoa! Okay, so clearly he is jumping a little bit too high here. This is probably around the time, we have a working jump. We can probably start adjusting the gravity and the jump force and get something feeling good, Let me see. All right. So let's dial up the gravity a little bit. Again, just so we don't have to be here all night, I kind of have in my notes good values for these. So we need a lot more gravity clearly. It looks like he's on the moon right now. So let's set the gravity to 55, and this should look pretty good, I think. There we go. That is a proper looking jump. We have one problem here though. So I'm checking if the fire button is pressed, right? The fire button's pressed, he's going to jump. If it's not pressed, he's not going to jump. Well, guess what? That means I could just hold the fire button. And he just jumps every single frame, as long as I'm holding down the button, because it doesn't care if it's, if I pressed it or if I'm holding it down. It's just checking if it's held or not. So we need to do something about that. We don't want you to be able to kind of moon jump like this. That's the other problem, actually. I can let go and repress jump, and even if he's in the air, he's just going to jump again. A little bit too much control for our character here. So let's fix these issues. And to do that, we need to keep track of whether or not our dinosaur is in the air, because if he's in the air, we don't want to allow him to jump again, right? So we're going to add a new address in air. And again, this will just keep track of whether or not he's in the air. And he's starting the game on the ground. So in our setup routine, we're initializing stuff with 0. We're also going to put that in air. He's starting on the ground. Okay. So now let's go back down to our check jump routine. And the first thing that we want to do here is, again, if the dinosaur is in the air, we don't want to allow him to jump at all, So if he's in the air, just exit this routine right away. That's the first thing we're going to do. So we're loading in air. And if it's not equal to 0, we're getting out of here. Okay. And we'll add some nice annotations or comments. And I'll add one here too. Okay. Yeah. It helps so much to have these comments for code readability. I mean, a lot of people have done programming in the room, so you know the importance of comments and all of that. But in assembly language, it helps a heck of a lot, trust me. When you're just scrolling through this code and your eyes are glazing over, it helps a heck of a lot to have good comments. Okay. So we took care of that. If we're already in the air, then we're not going to bother checking the jump or anything like that. But if we're on the ground and we press the fire button and we jump, we need to tell the game that we're in the air now, And to do that, we're just going to increment in air. So presumably it's 0 when they're on the ground. So when we jump, we increment it to 1. And that's all we have to do. Except for one last thing, which I almost forgot. Thankfully, I glanced at my notes. When we hit the ground, we have to say we're no longer in the air, set in air to 0. So again, I think that should be it. If all goes well, we should have fixed our problems now. We can't just infinitely jump in the air. And yeah, we have a good jump now. And I'm pressing the jump button, and it's not working. Now, I could still hold the jump button, and he kind of bunny hops like this just by holding the jump button. You can add some additional logic to check if you're like pressing the button or holding the button. But that is an exercise that we will not be doing today. So we're just going with the bunny hop physics, you know? Plenty of games have it. It feels pretty fun to do, so we're just going to keep it. Okay. So we have, I think we're done with our dinosaur physics, you know? We have the jump, we're on the ground. That's like most of the game. Except we need an obstacle now, right? We need something to jump over. So that's what we're going to do next. And that also means we need a new sprite, right? We need a new graphic, our obstacle graphic. So we'll make that the next sprite over. So the player is sprite number 1. Technically speaking, sprite number 0, because you know computers start counting at 0. So the obstacle graphic is going to be the next one up, sprite number 1. So that has an X and Y position as well. Vic is typically an organized chip who, you know, puts similar function addresses next to each other. So for all the sprite positions, it's like 0 and 1 are for the first sprite, 2 and 3 are for the second sprite, 4 and 5 are for the third sprite. So this is going to be our obstacle. So what else do we need to do? So in the setup, we have this little section, enable sprite, and we're only enabling the first sprite. Now we need to enable the first 2 sprites, and it's that simple. And now we need to set the sprite graphics. Pluralize this to graphics. That's the one potential downfall of comments, by the way, if you're a programmer, is comments can be out of date. If you forget to update them, then they might not actually reflect what the code is doing anymore, and that can cause problems in your code. So you got to be diligent about that as well. Okay, so we're going to take, and again, just like the player sprite, I set this up ahead of time. We're going to load the obstacle sprite, divide it by 64. Again, that's a quirk of the Commodore 64. And we're going to store that in the special place that Vic looks for our sprite graphics, which is 07F9, right after the previous one. Okay, so what else do we need to do? We need to set the color of the obstacle. So our dinosaur is dark gray. I know in the Google Chrome dinosaur game, I think it's just everything is black and white, right? Everything is gray. But let's make our obstacle, just for the heck of it, let's make it green. And that is going, let me see, I'm going to guess without looking at my notes that it's just going to be the next one up, D028. I was correct. And now finally, we need to set a starting position for this obstacle, especially since, you know, we just want to make sure we're doing everything correctly and actually draw it to the screen. So let's I don't know. Well, first, you know, just to make this a little bit clean, let's set the player sprite position, and now I'm just going to, in a separate section, set obstacle sprite position. Let's I don't know, let's do 200 for the obstacle X, and we want to put it on the floor, right? Same as the player. So max position, store the obstacle's Y position. Okay. So I think if everything goes well here, the obstacle, it doesn't have any physics or anything like that, but we should have set the position of the sprite and the graphic and the color and all that. So let's see if this works. There it is. It's a little cactus. Isn't that cute? Okay, but we need to make this move towards the player, give us something to jump over, right? But we've done much more complicated physics routines. We have jumping, we have gravity, you know. This just needs to move at a constant speed. So it should be pretty easy to do this, right? In fact, just for simplicity, we're going to do this as simple as possible. And, you know, if I was shipping a game, I'd probably make it a little more complicated than this, but, you know, it works for this demo. We're just going to decrement the sprite position for the obstacle. Subtract 1 from it. And now we have a new routine called obstacle physics, so let's go back up to our main loop here and just put this in, like here, for instance. Okay. So we should now have a moving cactus. There it goes. It's a little bit slow, actually. So let's, I don't know. Let's decrement it like a few times, right? Let's just grab this and like, I don't know, do that. So now it's moving 3 pixels a frame instead of 1 pixel a frame. Let's see how that looks. That's pretty good. Okay. We can jump over it. Nice. You'll notice one quirk. It's like when it's wrapping around, it's kind of appearing in the middle of the screen like that. That's something that, possibly to your disappointment, we're not going to fix in this demo because that is... you have to get just the tiniest bit more advanced with Commodore 64 sprite hardware, and in the interest of time, I'm not going to be doing that because we're already like over an hour in here. But it has to do with 8-bit values only going up to 255, right? Well, the screen is about 320 pixels wide, and so that's why it's going to 0, looping back around to 255, and it's kind of appearing in the middle of the screen for that reason. There's a special, Vic has another special address somewhere that you can say, hey, we're past 256. And so treat it like that. But it just requires some additional math because then you have to, you know, when you're past 256, you have to set that special flag. So we're not going to deal with that in this demo. Okay. But you know, at this point, we're almost done, right? I mean, we have the cactus, it's moving, we're jumping over it. I think the very last thing that we have to do is collision. And I guess we need like a game over, right? So... the thing about collision is, well, it's not the easiest thing, right? You know, we're gamers in here. We know about hitboxes and all that, right? Typically, there's like a rectangle, and you got to check: is this position? Is it like intersecting this? You know, is it kind of greater? Like, is the left side greater and the right side is less than? Is the top greater? Is the bottom less than? To see if they're intersecting. Guess what? We don't have to do any of that because Commodore 64 has built-in sprite collision. When 2 sprites are overlapping, Vic tells us. It just sets a 1 somewhere saying, hey, these 2 sprites are overlapping. It does all the work for us. And this is one thing that I love about retro machines. It just handles this collision for us. And it's pixel-perfect collision, which is pretty awesome as well. So that's going to make our job a lot easier here, and it's going to prevent me from keeping you all evening. But let's, before that, let's just set up a little game over address here. So we'll make it address number 7. This will just, you know, when the game is over, we'll just like make this a 1, and it'll tell us that the game's over. So down in the setup, we're initializing some variables. Let's just rename this to variables because it's doing more now. And we are initializing game over to 0 because the game is, in fact, not over when we start the game. Okay. Now let's go all the way to the bottom, and we're going to have like a game over routine. Again, every routine ends in RTS. If you forget to put the RTS here, then it actually just keeps going. You know, like when this code is done running, it just keeps going and it goes straight into the next routine. You don't want to forget that RTS. I've done that plenty of times, and it's always a head scratcher when you have those sorts of bugs. Okay, so what do we want to do when the game is over? Let's set the border color to red. It's a nice friendly light blue right now, so when the game ends, let's set it to red, saying, hey, you screwed up, loser. So we're going to load red. And we're going to store it in the background color address, Vic's special address for the border color, I should say. And we also want to set that new game over address. We want to increment it to 1. So that's our game over routine. Okay. We also have to check our collision, right? So we're checking collision. Again, Vic has a special address that tells us which sprites are colliding with each other. So it takes hardly any work. All we do is load this special address that Vic has. And we're running it through our AND. Similarly to the joystick, we want to filter out only the value that we care about. And again, this is like, if you go to like the C64 development wiki, whatever it might be, it'll tell you about this. It'll say, here's the special VIC address for collisions, and here's what all these numbers mean. Like, here's collision sprite 0 with sprite 1, sprite 0 with sprite 2, etc. Like, all of these have sort of different collision parameters. I know for a fact that this one is checking if sprite 0 has collided with sprite 1. Those are only 2 sprites, so this is the only one we care about. So if this is 0, no collision has happened, then we want to get out of here. So we do that. Same as before. But if a collision does happen, then we want to run game over. And that's it. So now back in our main loop, we just have to check the collision, and that should be it pretty much. Let's go up here. Main loop. And check the collision. There's one more tiny little detail, and that is if the game's over, we want the game to stop playing, right? So we're going to check game over, we're going to load it, and if it's not equal to 0, well, the game's over. So we're just going to skip the entire main loop, do nothing. Yeah, and that's it. If I did everything correctly, we should have proper collision testing and a game over sequence. So we're jumping over. I'm going to let the cactus hit me now. Boom. There we go. The border turns red as we set it, and the game's over. All right. We're done. Ship it. Ship it. Or as they would say nowadays in 2024, right? That's the state of things nowadays. But yeah, I mean, we have a working game. So I mean, we're here for a little over an hour, and it's a simple game. It might hold your attention for 30 seconds, but the most important thing is you hopefully had a pretty good understanding of everything that was going on here. Every little instruction and line of code I was doing, explaining how it was getting sent off to the computer and the video chip and all of that. So that's kind of my goal here. It's to demystify the whole thing, to demonstrate that it's entirely possible to do these things. We're given the tools to do it very quickly, and it's within our possible realm of understanding. It's not black magic, honestly. And there's great reasons to be doing this. There are excellent communities. Again, if you're an aspiring game developer, it is a possible way to get more attention than just your typical game would be, because these people are so enthusiastic. And people have found financial success making these games. If you're interested in selling your game for money, yeah, there's a couple great examples of that. Let me see. Oh, there's my demo. Yeah, here's one example. Has anyone heard of Micromages for the NES? No? A couple people? Okay. This game came out in 2019 for the NES. And it's a pretty dang good-looking game. Looks like a modern indie game. The graphics are great. The controls look pretty cool. Yeah, this game came out in 2019. They had a nice Kickstarter campaign. They had like a boxed version with physical cartridges. You could actually get this for your real NES. It was awesome. But aside from that, they put this game on Steam as well. So you can buy this on Steam, and you can play it in Steam. But you also get the ROM file if you want to play it in your own NES emulator. And that's another interesting point about these retro games. You make a game for NES. You're targeting one platform. That platform is never going to change. 10, 20, 30 years from now, there's going to be working NES emulators for our computers and our, tablets or whatever, our VR headsets, whatever we have in 2050. There's always going to be working NES emulators, and your game is always going to work for those emulators no matter what. But meanwhile, we're seeing a ton of PC games from even as recent as 10 years ago are just not working anymore on modern systems because of these compatibility issues. Hardware keeps changing. But retro systems are eternal. They're always going to work. And just like the Mate is doing amazing work preserving all of this old hardware, your game can be that much more easily preserved if you build it for a retro system. So I think that's another great reason to do it as well. Yeah, what's up? You emulate it. That's honestly all you have to do. Like, why would you do it any differently? NES emulators, they're extremely tiny, They run perfectly. They use such little resources. I mean, they were emulating NES in like 1995 on your Windows 95 PC. It takes almost no resources. So you don't need anything better than that. That's how you do it. And the player doesn't really need to know that, right? You just sort of have it transparent in the background. It's wrapped in an emulator. You can give them a nice little interface, controller configuration, and all that. That's all. And these emulators, a lot of them are open source. They're like MIT licensed. You can do whatever you want with them. You can package it. You can make whatever changes you need to it. I think it's a great way of doing it personally. Yeah, and then here's one more example. I mean, you saw me put together this this dinky little game for Commodore 64. This game was made in 2017. This is probably what you would call the best of the best in these modern homebrew retro games, especially for C64. This game is really dang advanced. And again, Commodore 64 came out in, 1983? I mean, it predates the NES, but this game looks incredible. It has four-way scrolling, full-on adventure platforming. You can pick up and throw stuff. There's like transformations and stuff. Really expansive game. But again, this was made by just the absolute masters of the system who were probably programming for decades on this thing. So they know every trick in the book. But I just wanted to give you an idea of the stuff that's happening in the scene and how people are making these games that they look like modern indie games. I mean, especially Micro Mages that looked like something that someone would build in a mod like Godot or Unity or something. But no, it runs on an actual NES, and and it's fun like a modern indie game. So that's what we're getting nowadays. There's a ton of people doing this, and the resources. I mean, there's so many I can't cover them all. I know one that is taking off it's called GB Studio. Yeah, it's effectively. I haven't really messed with it myself. It's effectively like a game maker, but for Game Boy. So you're not starting from a blank slate and coding assembly directly into a VS Code like this. It actually gives you sort of like a little game maker studio to make Game Boy games. It's really cool, and people are making good stuff with GB Studio. It's pretty powerful and advanced. So that's another great example. There are some people are building like sort of purpose-built programming languages for these old systems. If you don't want to write in assembly, if you want just the next level up, basic programming things like if statements and loops. People are have languages like that sort of just are one step above assembly to make that a little bit easier. And again, there's communities everywhere for these things. Discord servers. Subreddits, forums, for every single system imaginable has an active and thriving game dev community full of passionate people who are willing and interested to help you out if you're interested in getting started with this as well. But I think, that's pretty much my pitch here. That's the end of my presentation. Hope you enjoyed. It's always a lot of fun showing this sort of stuff off. And that's all I got. So how about we go to questions and, do like the applause thing or whatever, because Thank you. Okay. Yeah. Anyone have any questions? We'll, for the time being, just like about kind of retro game development or maybe stuff that I'm doing in the scene, just stuff that I did here that you might not have understood. Yeah. All right. You asked what instruction set the architecture this uses. So what type of CPU does it use? Because all the different CPUs, they have different flavors of assembly, different instruction sets, Like this one has increment and decrement, like this. Some other CPUs you might have to say add 1 or something like that. This is 6502, which if you're an enthusiast, you might recognize that CPU because it's the same one as NES. And it's the same one as Apple II. And it's the same one as Atari 2600. All of these systems have the same CPU, and so you're writing the same type of assembly language on all these systems. The other details are different. You're not talking to VIC on these other systems. They have their own graphics chips, their own way of doing things. But the flavor of assembly is the same. They're all running the same CPU. And honestly, it's kind of amazing because Atari 2600 is a piece of junk and it has the same CPU as an NES, So go figure on that. But it's because the other chips are way more advanced on NES, and that's what really drives the graphics and all that. But yeah, to answer your question, this is a 6502 flavor CPU. What's up? Yeah. Yeah, if you want to look at the... Typically, there's going to be like a wiki, like you could, like C64, like development wiki. Or I know for NES specifically, there's a wiki called NES Dev that very, very thoroughly explains every single thing you could ever want to know about the NES chips. Another good way of finding them is the magic word hardware registers. That's oftentimes what they're called. So C64 hardware registers is a good way to do it. But the information is so abundant that I don't need to point you to some special resource. It's like you put in these search terms and you're easily going to find a comprehensive resource on them. Or you could go old school and just buy like a development book from the 80s because there were textbooks that just lay it all out for you as well. Yeah. Commodore 64 does not have separate memory for both. It is C64 allows you to do a lot of custom memory mapping. You can specify like where you want the sprite graphics to be, where you want the your tile set to be, for example. And it's called the Commodore 64 because in total it has 64K of memory. Although I think that's technically including like the kernel, which is like a ROM that has some memory mapped to it. I don't remember because I'm not an expert on Commodore 64, but it's pretty freeform like that. That's actually kind of a big difference between like 8-bit computers and game consoles, because game consoles always have a cartridge with a ROM on it, but computers are a lot more freeform. You're typically loading your program like into the computer's RAM in order to run it. And so there's a lot less separation between the two because of that. You can kind of choose where you want to load the program into. You can choose what you want to make your working memory. And some lunatics even make self-modifying code as well. That's actually pretty common on these systems. If you're experienced enough to like get maximum performance, part of your code can actually modify instructions elsewhere in your code as it's running. It's pretty nuts, but yeah, that's what people are doing. I hope that more or less answers your question. Yeah. Yeah, so your question is if are there any retro systems that have good support for higher level languages like C, for example, and not just assembly. So the first thing is I mentioned that there are a couple of languages that people wrote that are sort of intermediary. It's not at C's level, but it sort of helps to simplify assembly and like cut down on the repetition. As for something like C, once you get to 16-bit, that kind of opens the door to C and higher level languages. So you're looking at Macintosh, Amiga, Atari ST, and in some cases Super Nintendo and Sega Genesis. People have put together development kits that are primarily C-based for these systems. But the other ones that I mentioned, the computer platforms, their operating systems, at least in the case of Amiga, the operating system was written in C. And there are C functions in order to interface with the operating system. Like you want to load a file, you can actually, ask the OS in C to load a file. It has like first-class support on those systems specifically. Game consoles are typically being done in assembly, but again, people have put in work to create either intermediary languages or dev kits that can compile C. You can compile C code to Commodore 64. It's probably just unwise to do so. You're not going to get very good performance in doing that. But yeah, if you want to write in C, definitely look to the 16-bit platforms. I think you'll have pretty good success. Yeah. So what kind of debugging tools exist? The debugging tools are getting quite good. Let's see. I can't show it off. I didn't get it to work before this talk. There's just something wrong with my configuration. But VS Code, for example, has built-in debugging support. I can set a breakpoint here. And and you can even see, look, the extension puts .break here. So presumably when I build and run this program, it remembers the breakpoint and can send it over to a debugger. It has pretty good support like that. And then there are other extensions, software stacks that if some emulators actually have remote debugging support built into the emulator and can talk to VS Code. So you can actually set breakpoints and step through in VS Code, look at the register values and all that. It's really comprehensive and typically quite easy to set up. Like for the Amiga game I'm working on, I do have a comprehensive debugger set up for that. And it's all modern tools, right? It's effectively like running the VS Code debugger and stepping through the code and stuff in VS Code while the emulator happily cooperates with that. It's gotten really advanced. People are doing amazing work in that space. Yeah.
I imagine creating those sprites take a lot of time. Are there live sheet libraries or places you could go to just find basic shapes, things like that?
Yeah. So you're probably imagining they take a lot of time because I opened up this graphics file and you saw that I drew the sprites with zeros and ones. Yeah, you don't have to do it that way now, because this is a demonstration that the data is made up of zeros and ones, right? But if I could put this in another file somewhere, and then there's going to be a directive. It's going to be something like inc bin, or not necessarily that for this flavor of assembly, but yeah, typically there's a little directive that just says take this external file and stick it in there. So yeah, if I had this data in an external file, which opens the door to I can use a sprite art software, a sprite or something like that, and export it into a file that the Commodore 64 understands, like these ones and zeros. Yeah, then I could just import the file and it significantly improves the workflow. Yeah. So something like those sorts of data hazards, it is, I guess in short, there's this isn't being compiled. The assembly instructions that I'm writing are literally telling the CPU exactly what to do at every step, and it's procedural. It's single threaded, just going straight top to bottom. So if there's going to be so there's probably not going to be an invisible bug like that unless you wrote the bug yourself in the CPU instructions. there are some platforms that actually do some stuff in parallel. Like the Amiga has a parallel chip that helps with graphics, like copying graphics from one spot to another. And that might be actually where you can hit some interesting errors depending on the timing of how long that operation takes, because the CPU is still going during that time. And maybe you can run into stuff like that. But yeah, typically just given how low of a level you're working at and how simple these machines are, bugs are going to be caused more directly by what you're doing with the code. I guess you could set up like CPU interrupts and have like a pseudo multi-threading going on, but you're getting pretty dang advanced at that point, and I think once you reach that point, you kind of know what you're getting into and understand the precautions that you can take to avoid these things. I hope that more or less answered your question. Yeah. So you mentioned how collisions was kind of like built into the hardware, and was wondering what sorts of other special features these platforms might support that are specific to games. And it's pretty vastly different depending on the platform. And as a matter of fact, a lot of more advanced games don't even use that sprite collision like hardware feature, because they're doing pretty advanced stuff like maybe reusing sprites. They draw a sprite up here, and then farther down the screen they clear that out and draw the same sprite down there, and it looks like two sprites, but it's not. Or maybe sometimes the sprite collision is you can't test literally every sprite to every other sprite. I'm not even sure if Commodore 64 can. I haven't reviewed it in a while, but the sprite collision register that I was using, there's only 8 values here, right? But if you have 8 sprites, that adds up to a lot more than 8 if you're checking every sprite with every other sprite, So oftentimes these collisions are being done in software anyway. Another reason might be maybe you want the hitbox to be actually smaller than the sprite to provide some kind of lenience. But yeah, I guess to answer your question, I'm trying to think of just anything comes to mind, like a special feature of the chip that that's gaming specific. I think a pretty easy one actually is scrolling, right? Scrolling is something where, again, you can't redraw the screen every single frame. It just can't push that many pixels every single frame. The CPU is not fast enough. And so to get smooth scrolling, there has to be some kind of register that can shift the screen just 1 pixel left and right, up to a certain amount, up until you reach the next tile. And then you can update the tiles and move them all over yourself. So I guess that's one example. NES is pretty interesting in that regard. You can set the NES to do horizontal scrolling or vertical scrolling, but not both at the same time. And the graphics are kind of laid out to make that possible. But yeah, I mean, the farther in you go, the more advanced systems you get, the more special features they have for games. I mean, Super Nintendo has like Mode 7, for example. That's ridiculously advanced. Amiga has what's called the blitter, which is practically like a GPU that runs in parallel to the CPU, that's copying memory from one spot to another and performing like masking operations and shifting operations and all this stuff. That was effectively designed for gaming as well. So yeah, the list goes on. That's one really interesting thing about these retro systems, is they all have different special capabilities, oftentimes purpose-built for video games. And so when you make a game for these retro systems, you're kind of asking yourself, like, how can I leverage these, And it gives these games personality, when you ask yourself like how you can make use of this special set of features for this retro system, it's going to inspire you to come up with interesting ideas that you might not have had otherwise. So yeah, went on a bit of a tangent there, but that's what I got. Yeah. Yeah, so the question is, like, if we're shipping an Amiga game, for example, in the year 2024, like, Are we just putting it out there as a ROM, or are we actually going to and trying to sell a physical floppy disk, a boxed piece of software? And I think I mentioned when Micromages came out in 2019, they ran a Kickstarter and they did have a boxed version of the software with an NES cartridge, so you could actually buy a boxed copy. There are definitely companies who are really interested in doing these sorts of projects. As long as you can pitch your game to them and they like your game and they think it'll sell, they might work with you to put together a physical package for this. If you're asking Amiga specifically, the Amiga community is surprisingly huge, especially in Europe, and they would absolutely buy physical copies of this. But if you look at the other retro systems as well, people love having physical copies of games. I mean, it's really easy. Like every system nowadays, they have like their kind of flash cartridge, ROM loader, or whatever, but there is definitely a draw and a novelty to playing on the physical cartridge that's not going anywhere. People like doing that, and there's even more of a novelty to hold a physical cartridge or floppy disk for a game that was released in 2024. There definitely would be demand for this sort of thing. It's an amazing collector's item. I don't know. Kind of akin to vinyl records, I guess. Vinyls are really popular. Not everyone's putting them on a turntable to play them, but it's its own little piece of artwork, a collector's item. So that's where I think this space is as well. Okay. I think we can wrap up the main section of the talk here. Again, thanks everyone. Those who tune in on the stream, thank you as well. I hope you enjoyed this talk. We can get started with the after party, I guess. So let me see. Just let me know when you've ended the stream.